Hi, my name is Christine Simpson. I'm a graduate student at Columbia University working with Greg Bryan. I'm going to talk today about some work I've been doing on simulating dwarf galaxies, doing high-resolution zoom-in simulations, and testing different feedback prescriptions. And I should mention I'm only going to be at Columbia for like another week, and then I'll be starting a postdoc position at HITS in September. And so I should say we've had a lot of talks about dwarf galaxies. Heidelberg Institute for Theoretical Studies. I'm joining Volker Springel's group. Oh, sorry. It's down the hill from MPIA. So yeah, maybe I should spell it out. Okay. So, and I guess I should say, like, we've had a lot of talks about dwarf galaxies, and dwarf galaxy apparently means anything from 10 to the 11 solar mass halo down to 10 to the 8, which is huge range. So I'm going to be talking about things of the mass of Milky Way dwarf spheroidals. And so actually the background image is an image of one, which doesn't look like anything. It's Willman 1, which you can't really tell unless you count the stars. So these systems have very low baryon fractions, as we've heard. You can see this in the so-called missing satellite problem. N-body, cosmological N-body simulations predict many more subhalos than we observe. And then when we look at the baryon content of halos versus their circular velocity, not only do the dwarf spheroidals, which are the red dots, fall below the cosmic fraction, they fall below the fraction that most spirals follow, like the Tully-Fisher relation. So, and they do so in a very stochastic fashion. So what is causing this large-scale suppression? That was sort of the goal that we wanted to test. So last year I told you guys all about some very high resolution simulations I've done of a 10 to the 9 solar mass halo. This is published now. These simulations had a co-moving minimum cell width of 11 parsecs. So at high redshift we're getting down to a few parsec resolution, and our star particle mass is 100 solar masses. So this isn't star by star formation, but we're approaching the mass of a massive star, sort of. And we include a laundry list of physical prescriptions. This is done with an AMR code ENSO. I don't have time to go through all of these, but I'm going to be talking about the feedback a lot. So these simulations just included a very simple thermal feedback prescription. We just dump thermal energy into a single cell over 10 million years and see what happens. So sort of the main conclusions that we sort of found was that the suppression of star formation in this halo it was a combination of the reionizing background, UV background, and supernova feedback. So if our full physics models are the black lines, and these are just two massive progenitor halos. If you remove the UV background, the total gas fraction of the halo will dip, but it'll recover, like it'll reaccrete gas. So the supernova feedback will blow out, but it's not sufficient to keep it suppressed. If you do kind of the inverse, you take out the supernova feedback but include reionization, you get the same large-scale suppression of gas, like you get these photoevaporative winds, but you get these self-shielded clumps that survive in the center of the halos. And you need the supernova feedback to blow those clumps apart from the inside in order to kill star formation in this halo. So when comparing this halo to well, it was sort of hard to understand what halo to compare this to, what real galaxies to compare this halo to, because this is an isolated simulation. But if you compare it to the Milky Way dwarf spheroidals, the velocity dispersion of the stellar component is comparable for the luminosity that we form, and the half-light radius is comparable as well. What was kind of different was the star formation history. Like, we didn't really get much star formation past Z of 3, and our stars were way too metal rich by like a dex. So we were having too efficient recycling of metals into subsequent star formation. So what could be the culprit? Well, feedback is the obvious culprit, and we used a very simplistic model that just did an injection of thermal energy. And we think that the metallicity of these dwarf spheroidals is really sensitive to the feedback. If you look at the metals retained, or you look at the metallicities of star particles in these systems, these are observations from Kirby, the mass of metals ejected from these halos versus the mass retained, it's ridiculous. Like almost over 95% of the metals are ejected from these systems. So it's almost complete metal loss. So we wanted to just then go back to the drawing board on our feedback prescription. So the first thing, we were injecting this thermal energy over a long time scale, which is probably unphysical for the star particle mass we're using, because you know, in previous studies, like, you do this long injection time scale because you're simulating a stellar population that's, you know, 10 to the 5 solar masses or something. But you know, really, it's only, these star particles are only producing 1 or 2 supernova events. So if we decrease the time scale of the feedback injection, then we'll get a bigger jump in the temperature. That'll put you on a nicer place on the cooling curve, and so you would expect to maybe get less radiative losses. In addition, if you just look at simple models of supernova feedback, like from Chevalier, just from the 70s, 1D models, you know, at the resolutions we achieve, you know, a significant portion of the energy is still in kinetic form, you know, 25–30% or so. And so, you know, it's maybe, you know, just dumping it all thermally, maybe that's not terribly physical. So, so what we wanted to then do is do a model where we, rather doing a slow injection of thermal energy into a single cell, we'll do a quick injection of both kinetic and thermal energy into a little grid patch. And I won't go into the details. It's just a simple, you know, we adjust the velocity, the bulk velocities of the surrounding cells, such that it, you know, we can set a fraction of the energy we want to inject as kinetic energy. So, what does this look like? Well, we just wanted to just start with some very simple tests at high resolution, just to sort of confirm things are working. If you just sort of set off a star particle in a box of uniform gas density and energy, without cooling, you get this well-formed shock that goes out. With cooling, you know, it starts to sort of break up, and you know, this is a uniform density, so you know, maybe you don't believe this shock at 1 megayear, but whatever. And so this is assuming a kinetic injection fraction of 30%, 10 to the 51 ergs, background density of 100 particles per cubic centimeter, and a cell width of half a parsec. So we reproduce set-off blast wave pretty well. Like, this is just the shock radius over time. The green curve is the analytic prediction. This is without cooling, and all the black lines are different models with different initial kinetic energy injection fractions. And so I haven't differentiated them because they're all on top of each other. It actually really, at high resolution, it doesn't matter, the kinetic fraction. You always asymptote to the same behavior really quickly. If you turn on the cooling, the shock begins to lag the theoretical, you know, prediction at a certain point, but you still get this shock moving out. Of course, my simulations don't have half parsec resolution. This is just sort of to make sure we understand. You know, at high redshift, when most of our star formation is happening, you know, 4 parsecs might be a better number. So this is from the slide before. This is this is with the coarser resolution. And you know, we also did some tests with different solvers. So I was just showing you calculations done with PPM, which is you know, piecewise parabolic method. It's an energy conserving method that has pretty high fidelity. I should say the galaxy runs we did with this method called Zeus, which is just a simple finite difference method that, you know, is not energy conserving but is quite robust. So if you're going to run like you know, one of these simulations, you know, I've had problems running with PPM. I'll just say that for the galaxy simulations. But you know, not only do you get some artificial energy loss, you also get these weird asymmetries, which I'm not quite sure I understand, but you know, be that as it may, you can get different effects from these different properties. So if you then want to look at how does the energy dissipation depend on resolution. So here is just the energy we start with. The black is the total energy, red is thermal, blue is kinetic. We start with 10 to the 51 ergs, and then as cooling proceeds, we lose energy. This is the energy fraction, and so we test initial injection energies from 0 to 1. So there's 11 simulations on these plots. And so at high resolution, it actually doesn't matter, the initial fraction of initial kinetic energy. However, as you start to go to coarser resolutions, and I should say the time steps get bigger, so that's why they start at later and later times, you start to see things start to change a little bit. So this is at 2 parsecs, this is at 4 parsecs, and here you really start to see a difference. The black lines, the amount of energy retained in the gas, depends very much on the initial injection of kinetic energy. And then at 8 parsecs, you get the same effect. So it matters, the injection of the fraction of initial kinetic energy matters at coarse resolutions and also at high densities. So how can we kind of understand this? So we can think about this by considering sort of the timescales for evolution of these supernova bubbles or supernova remnants. There's sort of 2 physical timescales that you can consider, what I'll call the equilibrium timescale, so the timescale at which the set-off phase would begin, which analytically you expect to happen when the mass of swept-up material is twice the ejection mass, and then the time at which the snowplow phase begins, and I'll just sort of estimate that when you get a loss of 30% of the initial energy. And so these are like physical timescales to do with the problem, but of course we're simulating this, so we have to also consider numerics. So I'm going to sort of estimate what I'll call a resolution timescale, because you need like a well-formed shock for these timescales to sort of make sense. So the timescale at which you sort of get a well-formed shock, I'll estimate that at the time at which the shock, what I call the shock, it gets to fill 3 times the injection volume. And so the blue is the resolution timescale, and I'm doing simulations at various resolutions and densities going from 1 particle per cubic centimeter to 1,000. And so basically, as you go to denser material, the resolution timescale starts to exceed the cooling and the equilibrium timescale, and when that happens, you get a large dispersion in the snowplow timescale. You start to get a dispersion in the snowplow timescale and the equilibrium timescale, and so basically, that's what that's telling you is, if you lock up more energy initially in kinetic energy, you will get an effect in the behavior. So we have done some initial preliminary galaxy simulations with this, like with the halo I showed in the beginning. And these are very preliminary. And so we're just creating single supernova events. We inject the energy promptly in like a single time step. And we also have the issue in these AMR codes that, what do you do if your star particle is at the edge of a grid and its neighboring cells are on another processor? Well, there's been a large push in the ENSO community led by people not me, Nathan Goldbaum and John Wise and others, to sort of solve this problem. But until that is fixed, what I've just done in these runs is I've just slightly shifted the feedback region, which is a cheat, and that's why this is preliminary. But I'll try and wrap this up. But we sort of done this, and we've gotten some interesting results. The star formation rate does change, and not only is it different from our old model, okay, 2 minutes, it's also different between each other depending on how much kinetic energy you inject. So 0%, so it's still a thermal model, or 30% where you do 30% kinetic. And so what we find is when you include the kinetic energy, you get a large suppression of the star formation rate just off the bat. And I think that makes sense because I think we're at the resolution regime where this matters, right? And so I'm kind of curious, if we were able to push down to, say, parsec resolution, would this hold up, or would you see these two converge? Also, you see just doing two purely thermal models, but one is prompt injection and one is slow injection, you get a difference. So somehow when you have this slow injection where you're constantly injecting energy, even though the total amount of energy you inject is the same, you get a faster truncation of the star formation history, whereas you do get some continuing star formation in the prompt injection case. What's quite different though is the metallicity of the star particles. So basically in these models with the new method, almost all of the metals are ejected, and we get a mean metallicity that's much more reasonable and actually might be a bit too low. So this is the new model that's just purely thermal. So this is just showing you the effect of prompt injection, or quick injection rather, not quick injection. If you do it with the kinetic energy, you don't get these low metallicity particles. It's a much more narrow distribution, but it's actually roughly kind of the same mean. So the momentum actually doesn't really make a difference for this observable, for these preliminary runs, I'll just say. And so, and actually this level, I think you can basically explain by the assumptions we've made for the yields and the amount of mass that star particles are returning to the ISM, basically, and the densities at which we're injecting this material. So I guess I'll try and wrap this up. These are sort of obvious things, the first couple things. Feedback plays an important role in shaping many of the dwarf properties, and resolution is really key. And also, we need to consider multiple observables to understand the feedback. The star formation histories, the metallicities, complex abundance patterns, central densities. Like people tend to have their favorite observable, and it's not, we need to think about it holistically. And then, some of these observables are affected by certain aspects of the feedback more than others, I think. So it's important to do runs where we try and test this by taking things out and putting them in and, testing them out. So there'll be further code improvements, and thank you.
I was just going to suggest that the funny shapes you were getting in the Zeus run,
Mm-hmm.
probably because it's a directionally split integrator.
Yeah.
And so it gives you, so what you get actually will depend on whether you're in a time step where you're doing the X, Y, Z or the Z, Y, X.
Oh, okay. So I know Elizabeth Tasker had done some runs with Zeus a long time ago, and she saw this diamond shape. And then I sort of wondered, because I actually didn't center the star particle exactly in a cell. I put it a little off center just to test the cloud and cell algorithm. So I thought it was, but that makes sense. Okay.
That you see that very frequently in directionally split.
Okay. Okay. Oh, okay. Well.
I had a question about the multiple populations which are sometimes seen in dwarf galaxies.
Yeah.
So a burst of star formation, then 5 dB is nothing, and then another burst. So
I know.
if you have your feedback too efficient, you can't get multiple populations. So you need a fine-tuning to keep a little bit of gas around.
That might be the case. I mean, the other thing is environment. I mean, we know, this is one halo realization where I've tested these things and,
But if the environment plays a role, then stripping could be more important than any feedback. Then the whole physics changes, and you don't have to worry about supernova anymore because you strip the gas simply by moving through the environment.
Yeah, that's also true. I mean, yeah, I'm also puzzled by these galaxies that do nothing for gigayears and then suddenly there's something. Yeah, I think it is a mystery.
But just to clarify, you got dwarf spheroid galaxy
In isolation.
in isolation.
Yes.
And you think that's reasonable?
Well, I mean, observationally, I don't think we have deep enough surveys to really test whether these exist or not. I mean, we do? Okay. They don't? Okay. Okay.
That, this is what you get from simulation. You get simulation.
Well, I mean, I was really intrigued by some of the simulations of Piero Madau's group where they were forming these dwarfs with a large reservoir of H1 that doesn't form stars, and yeah.
Which is exactly what galaxies are doing.